All right, so let's see where we left off. As you recall, it's like we've been trying to prove global convergence of an arbitrary one-step method. And what we established was an error recurrence, which the global error satisfies, that the error at the end plus first stage is some multiple of the error at the end stage, plus some term here, which is the local truncation error. And what we're going to evoke, of course, is the discrete Gronwall lemma, which exactly states that if you have an error recurrence of this form, that you can establish estimates. It's like on what the error at the end stage is. Okay, so so now what we're going to do is we're going to apply it's like the discrete Gronwall lemma to this specific sort of inequality. It's which we established, and it's easy to show, of course, that A is nothing more than 1 plus h L hat, right? And B here is equal to c bar h to the p plus 1. Okay, so so when you apply discrete Gronwall, and what you obtain is that the norm of the error at the end stage is going to be bounded by c bar h to the p plus 1 over kappa, okay, minus 1. So I'm going to call this term here kappa. Okay. All right, and then this will be kappa to the n minus 1 plus it's like kappa to the nth power, the error at the 0th stage. Okay, so it's worth like mentioning, of course, that when you are using a numerical method, what you in order to solve an initial value problem, then usually the assumption is that the solution at the initial time, okay, is exactly just the initial condition. So the error at the 0th stage is going to be 0. So this term is going to vanish, and you're just left with this estimate here. Okay, so this is going to look like nothing more than c bar h to the p plus 1 over h L hat, and then you have this again kappa to the n minus 1 term. Okay, so what you're going to do next here is that you're going to look at this kappa term. It's like to the nth power. So you know that kappa is 1 plus h L hat. Okay, so in particular, you know that if you look at the exponential of kappa, okay, so if you look at e to the kappa, actually, I'm sorry, you should look at e to the h L hat. Okay, so you look at e to the h L hat, it's like then you know that there is a series expansion which looks like 1 over h L hat plus a bunch of higher order terms. And these higher order terms, of course, are all positive, based on the assumption that h is positive and L hat is positive. Okay, so what that tells you then is that kappa in general is bounded from above by e to the h L hat. Okay, so so what I'm going to do then is that I'm going to use this to upper bound this kappa to the n term. So this is going to be bounded from above by c bar h to the p over L hat. Okay, so I have a cancellation of the h to the p plus 1 term by a h in the denominator, and then I'm replacing this kappa to the n term by essentially e to the nhl hat. Okay, so this is e to the nhl hat minus 1. Okay, and so you can again bound this because n is the number of steps and then h is the step size. So together these this factor here is bounded from above by the total time of the integration. So this is less than equal to c bar h to the p over L hat, right, e to the total time times L hat minus 1. Okay. All right. So once you have that, then you're in business. So this basically proves the following. That, so you've established the following theorem, which is that the global error satisfies the following. That if you look at the maximum over every single time step, so n equals to 0 to big N of the error at the nth stage, okay, then this thing is big O of h to the p. Okay, and so the basic idea is that now you have a uniform estimate, right? And which you can then show what happens. It's like when the time step h goes to 0. Okay, so let me just stop here.